So, region bounded by the graphs, x squared equals y minus 2, 2y minus 2 equals 0, x equals 0, and x equals 1. Well, these two, if we didn't have this here for us, we would definitely need to solve these for y so we can graph them. And it's kind of done for us already. This first one is y equals x squared plus 2. Right? We have this parabola here. Then this, we just have a line, it's y equals 1 half x plus 1. So that's already done for us. And then we have the lines x equals 0, x equals 1. So we're looking at this region right here. Since we're rotating this around the x-axis with disks and washers alike, if we go around the x-axis, we're going to use a dx cut. So we have a dx cut that we're dealing with here. And we are going to have this little rectangle that gets rotated around the x-axis. Now, we have this picture given to us, but most cases that's not going to be the scenario. And we've dealt with discs and now washers, and then we're going to talk about shells later on. So it's good to get in the habit of kind of, all right, look at my picture. What kind of cut am I using, dx or dy? What shape am I getting? What kind of cylinder are we dealing with? Is it a solid cylinder? Is it one with a hole in it? Like I said, you can see that here, but just for future reference, what I would do is just kind of draw x and y coordinate plane and our rectangle, kind of the way it looks. We're spinning that around the x-axis. So for those of you that are graphically challenged, you can take this rectangle, draw one just like it, below the x-axis, about the same distance, kind of like the reflection of it. And then what you can do is the bottom and the top here, connect those with kind of like a little oval. The top of this one, bottom of that one, connect those with an oval. And then you can kind of do like that to give it a little depth. So from this picture now, we know, okay, there's a hole in the middle. Another way, you can tell if there's going to be a hole in the middle. If it's not touching the axis of revolution, there's going to be a hole in the middle. But, like I said, there's one other type of volume that we're going to do using shells. And shells are kind of similar to washers. They're cylinders with holes in them, but they're a little bit different. So, trust me, once we get there, it's going to help you to kind of visualize this if you make this little drawing off to the side. It also helps you, it may help you, to look at what's our little radius, what's our big radius. Right? The little radius goes to the bottom of that rectangle. So if we translate that up here, this is our little radius from the x-axis up to the bottom of the rectangle. Well, the bottom of the rectangle is always going to be on this function. It's always going to be on the line y equals 1 half x plus 1. Our little radius is a y value, right? It's a vertical distance. It's like a y value because we're going from the x-axis up to this point. So it's the y value on this curve. But we're using a dx cut, which means we have to do everything in terms of x. So we can't just say the radius equals y. We have to say the radius is equal to what y equals in terms of x, which is 1 half x plus 1. So this is our little radius. The big radius goes from the x-axis to the top of that rectangle. And the top of that rectangle, can't see that so good, the top of that rectangle is always going to be on this graph. Right? So it's the y value from x-axis to this graph, but we have to do it in terms of x. So our big radius is going to be x squared plus 2. So once you know big radius and little radius, we can set up our integral. We have pi times the definite integral. What's our smallest x value? 0, right? Comes from those lines they gave us, x equals 0, and our biggest one is 1. And then we have the big radius squared, so x squared plus 2 squared, minus our little radius squared, times the height, which is going to be dx. Right? Remember, the height's always going to be dx or dy in these problems. So we can put this in our calculator. I'm not going to show how to do it. We've done it enough now. But if you do put that in your calculator, you should get 3.95 pi. Remember, I'll accept it if you multiply that out 3 decimal places, but sometimes you may need an exact answer for a multiple choice problem.